Hello folks, good morning. Thank you for coming here through the rain. As was mentioned, my name is Jules Glegg, go by she and her, and I'm the tech director at Soft Rains. I'm not sure about this, but my presence here might be a little bit of an aberration because I'm a game engine programmer. So we're going to unpack some of the zany stuff we've done in our video game, kind of a grab bag of interesting tech that has led to space fungus that you can clean away and have fun doing it. So, Soft Rains, we're an independent game studio right here in Toronto. Team size is about 12.5 for scale. And the game that we're talking about today is Ambrosia Sky. It's the debut game from our studio. I'm very excited to even have splash art I can put on a slide right now. For those that haven't seen the game, it is a single-player, first-person, science fiction, immersive, clean-em-up game, such as the giant compound list of tags that game genres have to have now. Or to put it, as PowerPoint said, it's Metroid Prime meets Power Wash Simulator. You're in space, there's a lot of horrible grunk for you to clean away. It's built with Unreal Engine 5, and we use Houdini engine a ton in our pipeline. If anyone's not used Houdini engine, this allows you to invoke Houdini from within other applications that don't have Houdini's powers, and just for a moment, steal and use the power of Houdini to your advantage. So, space fungus, the primary enemy that you will fight in our game. It is not your standard video game enemy, and the main way you'll interact with it is by, aside from being set on fire and electrocuted and all of those things, is by cleaning it away. So before we dive into the tech behind it, I'm going to show you a little bit of what it looks like and what it does, so you'll have a reference frame. Thank heavens the video worked. Cool, so you saw several species of space fungus there in the video. We've had to come up with kind of a unified pipeline through a smaller team to share a ton of systems and workflows between those and let designers kind of go crazy filling the biome of this weird world. The challenges we're facing, as I mentioned in the shorter talk before, is we like video games to feel interactive. Otherwise, it's not really a video game. So 60 frames a second is our target. That's 16 milliseconds every frame to do all of the work, physics, enemy behaviors, combat, audio, everything. Computers are fast, but they're not quite that fast. We set a 33 millisecond defect threshold, so that is if the game drops below 30 FPS on any target device, it's a bug. We budgeted, therefore, 3 milliseconds a frame for everything to do with fungus, roughly. It's a big chunk of our frame compared to all of the other operations that have got to take place. And we've got to do all that on a Steam Deck, which is a pretty capable little machine, but it is ultimately a handheld and not a LED'd out gamer rig that you have under your desk. So things in our favor. Well, as you saw, the art direction has a kind of large average object size. There's not a ton of fiddly detail like you get in a lot of space games. And the fungus, it's mostly staying where it is, right? If we want to chase you with fungus, we don't have to move the bits of fungus around. We just spawn more kind of at you, and the bits that we've already spawned can stay in place. And that's it. That's all we have in our favor. So the things making it harder for us. Well, the first off, As you might have seen from the video, it's quite a dramatically cast world. We need a lot of dynamic shadow, a lot of drama in our frame. And the puzzle design, as you saw in some of the immersive sim elements, calls for dynamic lighting. We're using lighting as an indicator as to the state of electrical appliances in the world. So, okay, we got to do the dynamic lighting. That means baked lighting is not super helpful for our game. And furthermore, although Unreal 5 has global illumination available, it's pretty expensive compared to the other things we need those resources for, which we'll talk a little bit about. So that's really not going to come to our rescue either. Existing AI solutions, I have put a wildcard next to AI, or an asterisk, sorry, footnote, because in video games, AI does not mean the thing you use to generate trail cam footage of Mayor McCheese. It is the enemies that you fight in the game. Just any non-player character we call AI. Finally, volumetrics, not even close, are heinously costly, can really, really add up. And when you go to kind of fix up volumetrics, you say, okay, let's like make it a little bit more coarse-grained, a little bit more granular. Our art director spits out his old-timey cigarette holder and says, no, we cannot have voxels in our game. If we're going to have voxels, it's going to be a creative decision, not a technical one. Or at least we can't have the appearance of voxels. So that's everything working against us, all the problems that we got to solve. Burns down to three kind of big buckets of problem. One is that colony tactics need to be solved, so how colonies arrange themselves, how they pursue their objectives, how they spread out naturally in the world. Just lighting as a whole needs to be solved. We've got a really tough problem space for lighting in our game, and our volumetrics, as mentioned, must please the eye and not be kind of the diagonal-faced, very clunky dynamic meshes that you can get with some voxel systems. So how we're going to set up our engine at the start of our project. We have relatively few highly detailed meshes. So we'll turn nanite, that's the engine's dynamic level of detail system, off. Big savings in our favor. Great. Tight interior spaces with an enormous object count. It's a stress test for global illumination. Let's turn it off. In any case, we found the global illumination kind of didn't give us the stylized appearance we wanted. It's a great system. I look forward to using it. Just wasn't quite a fit for this game. And finally, enormous piles of dynamic geometry that were spawning at you, kind of the main gameplay mechanic here, which means, pardon me, no baked lighting whatsoever. On the plus side, our builds are fast. So that's something we get back, but no baked lighting whatsoever. It's kind of fun to discuss. If you say, I've got an interior game, no baked lighting, people raise their eyebrows. It's a fair question. So fungus tactics. Typically, for our AIs in the game, we would use this thing called navmesh. Most game engines support it. It's this green blanket that's kind of draped out across the floor. The theory is that it's much easier for an enemy to query and traverse that geometry than understanding what a table is and that it should move around a table. You just have a hole cut in the navmesh where the table is. It really helps with traversing the world, but it does not help with tactics and behaviors. And swarm behaviors, you get really into them, they're a many body problem. Mathematically, they're pretty hard to solve. So we've still got to figure out our colony swarming behaviors. So we looked to nature and to science, and we found this cool algorithm called the space colonization algorithm. It comes out of I believe, the Algorithmic Botany Institute, which is part of the Department of Computer Science, which is part of Calgary University, and it mimics the distributive behaviors that biological organisms have when they're spreading out in search of nourishment. When branches grow and grow leaves in search of light, they try to find the empty spaces. When slime mold, as gross and beautiful as it is, grows across, it's looking for food and spreading out. So we'll have a little look at how that works. So, quick run through. We'll scatter food everywhere across we want things to grow. We'll call these points attractors. Easy to get started with in Houdini. Scatter points on a mesh, right? They've done that 100 times. We'll pick some to start, depending on the behaviors that we want. We could start at the outside and grow inwards. We could start in some random places. For us, we want to grow from an origin, so we pick some kind of in the middle. Then, for each node that we've identified, we're going to find the average direction of all of the food, all of the attractors around it, and move a fixed distance in that direction. When we get there, we'll create a new node and then eat all of the food nearby. And we're just going to do that over and over. So we'll do that for another point. Notice how this one distributes itself downward because the first one went up and ate the food, and now the weighting is different. So we're just getting pulled around in space. If you're asking, did she actually scatter all the points on the PowerPoint slide and run the algorithm by hand? Yeah, I did. I think, it's mostly right. It's close enough. Let's speed up the algorithm now. Run it, tick and tick. We're getting these beautiful distributed patterns. Here we've got something interesting. We've got a couple points that have ended close together. The algorithm doesn't guarantee that that doesn't happen. It just makes it kind of unlikely. And it's fine. It's totally fine for that to happen. We've also branched. Just because we grew from a node does not mean we removed it from consideration. If there's still attractors around one, we can still grow more points and branch off and fill the space that way. So we keep growing, and we get this beautiful distribution, beautiful natural distribution. And it works kind of good in 3D. This is one of our early experiments with it. It works pretty good, with some caveats that we'll get into. You can just scatter points around the outside of something, run with it. So our theory is, if we can take our level geometry, let's take this as a simulacrum of one of the levels in our game, we could send it into Houdini, using Houdini engine, generate these pathways across it, return that geometry into the game engine, and use it not as a visual asset, but actually as data inputs for our gameplay systems to help these AIs navigate the world. Because if one of them is moving on one of these line primitives that we've created, we just can mark it as claimed. And if you take an unclaimed one, and it's going in roughly the right direction, you're guaranteed that you're getting this lovely natural spread across the world. It's a gross mycelial version of nav mesh that in the end replaces the whole system. So I did mention there's a couple of caveats. One is what I'm going to call the thin surface problem. So it's not aware of surfaces and which ones you want penetrated and which you don't. So here I've made a very thin floor, and of course, because we've naively scattered points across the top and the bottom, we've got attractors within our search radius that are pulling us down and up, and we're zigzagging actually through the geometry. And look at this horrible thicket of line primitives we're getting as a result. So we kind of rolled with this for a little bit, and it was okay, but you're getting a lot of objects navigating outside of the world and through walls, and it's a little immersion breaking. So kind of go back to the drawing board on it. I neglected to talk about the bullets on this. It's fine. We covered them. So return to nature. Get more ideas. We started with nature. Let's go back. So if these food points represent nourishment that the fungus is growing towards, in the real world, the food points that come from somewhere, right? Come from the sun or moisture conditions or whatever. So we thought, okay, let's try an approach representative of this. So we exposed something we called growth lamps. And these are not as fancy as they sound. There's kind of no shadow casting involved in this or anything. It's just a handle that a designer can move around. And yes, the handles do appear in Unreal Engine for a level designer to manipulate. Bounding box handles and transform handles only, if I recall. Maybe some more in the future. That would be cool, but these were enough for our purposes. And all we're doing is killing any attractor that is not facing by surface normal at least one of the lamps that's turned on. and we kind of fix our problem. It's very easy for a designer to say, I want to grow on the underside and the side of this thing, and I want to grow on top of this thing. It's close enough for our level designers and fast enough for them to work with. Limitations, well, you can't, to my knowledge, if anyone knows, please shout out in the question time. As far as I know, you can't like dynamically add handles, especially if you're you have Unreal Engine between you and Houdini. So we just had to say, here's 3 growth lamps that you can turn on, and that's probably enough. And if you need a 4th, please make a Jira and put it in our queue. It's like not the solution I'm the happiest with, but it seems to work well enough. So speaking of level placement, let's look at as tool programmers, role-playing as tool programmers for a moment. What are our customers? Our level designer is going to be doing mad placements with these. Going to be dragging and dropping and then trying it in all sorts of locations, trying all sorts of room shapes. That's got to be fast. They've got to be able to just like blast the world with fungus. But once they find something they like, they're going to want a ton of dials and knobs and twiddles and ways to tune the placement that they've got that they're enjoying. So we've got to solve that for them as well. Our technical artist wants control of how we grow the fungus along these paths. They want to control the overall appearance, profile, and density of a colony of each species. And as a programmer, we want it to all go fast. Otherwise, the game will kind of suck, no matter how good all of the design inputs are. So this is sort of the problem space we gotta solve. These are our fixed points, and we came up with, in the end, I should have mentioned, sorry, everyone wants determinism, everyone wants the same result. If you spawn a colony in the viewport, in the editor viewport, and then you go in-game to play it and it looks totally different, the tool's useless, right? We've got to produce a consistent result every time. So in the end, this is our custom editor panel from when you drop a colony into the world. It's got a ton of options on it. This is a custom detail panel that we made using sort of the Unreal extension framework. It is capable of, here's something we ran into pretty early on. We were using the stock Houdini actor that you can just drop in, say like run this HDA. I'll fill in the params myself, and then I'll drop like a fungus spawner on and connect it to the HDA, and it's a lot of clicks for the designer, but it worked okay for a prototype. The problem is it was easy for the data to get out of sync between how the HDA is configured and the values that the actual gameplay code is using. It was pretty clumsy to read variables between the two, so guess what? People just didn't bother. They just put the number in 2 places because that keeps them going fast. And so in this framework, we're able to say, okay, we'll actually be the source of truth for everything to do with the fungus colony, and we'll selectively send some of those params over to Houdini, and we're assured that they're always in sync with each other. And I should clarify, we did this because suddenly we feel pretty good about the system, and we've got several people starting to block out levels at a pace, and we need to speed up that process and get out of their way. You don't have to start here. Like, don't start by making a whole tool until you know what your designers, your customers as a programmer are actually running into and what they need from it. It endured a few months of pain with shortfalls in our solution until we figured out, like, okay, I think we've got an idea what the problems we want to solve now. So for level placement, I mentioned wanting to just drag and drop these things. We set up just using stock engine features pretty much, something in the construction script. This is something that Unreal runs every time an object is placed or every time its properties are modified, so you can use it to do some lightweight procedural stuff. Think of it, the analog in Houdini would be having, just a node is kind of recooking as you modify the params to it. It's just handling some stuff off board for you. It is able to, once it's dropped in, immediately seek out nearby level geometry thanks to some conventions that we have in our collisions. And it's a tag-based workflow. So you can see at the lower end here, we've said, hey, if you tag your components in your levels, tag your meshes in certain ways, we can just have very consistent handling of them. You don't want fungus to grow on your chair mesh? Tag your chair, no fungus, the fungus system will just ignore it system-wide, no problem. Which, yeah, do people put typos in tags? Yes, but it's fine. Like, by and large, it works pretty well, pretty efficiently. So, spawning. Let's talk about this. I mentioned the tech artist wants to control the silhouette, and they don't want to have to do it by dropping down into C++, so we use Blueprint, which is Unreal's node-based visual scripting language. It is very similar to the user experience of creating node graphs in Houdini. The only difference is that there's a thread of execution rather than Houdini figuring out what order to execute things based on dependency flow. That's sort of the main difference between the two. For determinism, I forgot my programmer thesaurus for a moment, we slice the growth into discrete ticks. So if you wanted to grow 0 to 100%, we say, cool, but hold your horses. Let's slice that into, say, 200 discrete intervals of growth so that each tick can have its own deterministic RNG stream that is driven by some information about that tick, which unit of growth we're performing, and the seed that the designer chose when they started to place it, which means the results can come in the same as the tech artist uses randomization to pick meshes or to nudge meshes during the spawn. I also mentioned programmers want to handle the performance. This is one of the places we can get our hooks in. In this spawning blueprint, the tech artist uses two very important nodes. That's spawn fungus and release fungus. And those are transparently handling pooling, resetting the state, everything we want to be able to sort of build up a bunch of fungus secretly somewhere in the level and have it hidden and then dole it out to the spawner as it asked for them, which helps buffer some of the performance issues. And if you have been looking at these two pictures and thinking, why are these two pictures here? What is the difference between them? This is one colony shot from the same angle with two different spawns. I restarted the editor in between. So corporate does want you to find the difference between these two pictures, and they are the same picture. No differences came out, which we're pretty happy with. Okay, so here is a little demo, which hopefully will stream. I want to show you the editor workflow. I'm so confident in the speed of it. Let's do it in real time. I'm going to drag fungus into the world. I'm just going to blast it against that wall. I'm going to hit the details panel. We can control Houdini engine right from there. Some people have it set to automatic, some people don't. I want to say, let's spawn this directly at the player, right when the level starts, and I want it to come in over the course of 10 seconds, so to grow pretty aggressively. Hit play, bam, I'm playing my encounter. Do I like where it's placed? Do I like how it's interacting with the lights? Are there changes I want to make? Very, very quick for me now to start tuning this. Say maybe I don't want it to grow around here, out of the big volume. It's the real system. We're not faking it just for pre-visualization. It's the real system that the player would interact with in the file. So we got a pretty tight loop in there. We want to have very, very few clicks if we possibly can. Okay, so now we've got fungus tactics sorted. We can grow in deterministically. We can spread beautifully throughout the world, across walls, across ceilings. Now let's solve for lighting. So dynamic real-time shadows, quick primer for anyone that's not familiar. Shadow casting is a special, expensive luxury thing for lights and objects to do in the dynamic lighting system. Shadow casting lights are essentially cameras with all of the cost that implies. The background of this slide is actually the view from the perspective of a shadow casting light, where it's just rendering a depth pass of one of our fungus colonies. And the cost of that light scales with the complexity of that scene, which means all of the objects that are shadow casting that are included in the scene, the range of the shot, our culling distance, all of that stuff, and also our geometry shaders, because we want to see the final shape of an object to determine if it's going to cast shadows. So these things can be pretty expensive, and we spawn a ton of fungus. I think some of our levels have maybe 12, 15,000 fungus meshes spawned in them at peak. So they can get pretty expensive, maybe 8,000 in our worst case run. I think it's the best case realm because it's got the most cleaning to do in it, but it's worst case for performance, right? So we developed this approach, which we just called like shadow culling. It's just a voxel-based shadow culling. So what we do is we break space up into discrete grids of a particular size that can be driven by the performance settings of the game. And we say, okay, like this region of space, each region of space, a certain number of fungus meshes are allowed to cast shadows on a first-come, first-served basis. Nothing super fancy, figuring out what's the best spread, just first-come, first-served. It mostly works fine. Even at our max settings, we still use this, and it's sort of an average saving. We cut the number of shadow casting meshes in half. Most of these meshes don't need to cast shadows because of the way they're clipping into each other, which is a deliberate feature of the visual design. And it's totally fine. We just get a ton of frame time back. On our medium settings, which is how we run on our baseline platform of a Steam Deck, we tune this a little bit more aggressively to say, okay, let's 3 can cast a cell, and you can see in that image there's a little bit less drama in the scene, right? Like it's clear the directionality of the light. There is some looming successfully happening at the bottom of the frame, but we're missing a little bit of richness in the middle, and that's okay. The player's choosing a lower fidelity to increase their frame rate. It's okay. We would rather they have that than to be chugging along in the game to not feel responsive for them. Another issue is, okay, you're culling all your shadows, but if your objects are right next to a light and they're not casting shadows, it's going to look kind of goofy. It's going to pull the player out. They're going to be critiquing the frame and thinking, what choices did these developers make to saddle me with such a hideous frame? So we do light forgiveness as part of our performance settings as well. That is, if we're in a region of space that is within a certain radius of a shadow casting light, we can dynamically say, okay, you can have a few more objects to cast shadows to create some drama around this object. And here is, again, it demonstrated on max and medium settings. Well, like max is creating a ton of these beautiful long sunset shadows. It looks great. Medium, we're getting some. It's enough. Like we're getting the idea. We're not the happiest with it, but again, the frame rate is staying high, and it's worth the trade-off for that. So aside from that, our approach to lighting performance goes straight back into your regular engine profiling, just looking at your big lights, the ones with the long attenuation radius, managing how many are in the sight line. Once we had fungus tamed like this, it became a sort of a stock game development optimization task. Okay, so the meat of the matter, volumetric cleaning. Let's talk about this. So, the idea that we were having is if there's these things called vertex animation textures that can offload a pre-simulated animation totally to the GPU with no CPU cost, that feels pretty attractive to us because we've got to do like potentially hundreds of these in the frame at the same time, and skeletal meshes are crazy expensive at that count. There's also these things called conditional VATs where you can inform and manipulate the VAT animation. At a cost of texture memory, you gain some interactivity, some responsiveness. There's a pretty great example of this that's on the side effects learning resources. I'll throw up a QR code there so that if you want to check it out, you can. We thought maybe we can take it further. We'll have a volumetric conditional VAT where we just spend enormous amounts of texture memory, everything we're getting back from not using global illumination, everything we're getting back from sort of the hand-painted textures in our game that don't have to be 4K, where we don't have like guns with 2K textures. We're not in that design space. So this is where we're going to spend the texture memory for our game, is on volumetrics. So the idea then is maybe we can capture places where the sprayer, your primary weapon in the game, impacts the world. Take those impacts and quantize them. Make them granular in space so that we can keep track of them and store them in a field. So we're going to have the ability to query any region of space to determine if cleaning has happened here and change our rendering accordingly. And that's what we did. We never intended for this name to be like a public branding of the technology, but it describes what it is. We abbreviate it to KIF, like the little green guy in Futurama. So we started trying this. It was a zany idea, and we took a couple weeks aside to see, can we make this work? Can we make it work well? You see our first version is super janky, right? We've got like texture buffering problems. It's not quite working right, but it proves a concept. So we took it a little bit further and said, well, maybe we can animate based on this. If we write into a texture like the times at which the damage occurred, maybe we can use that as a basis point for a transform and start warping the geometry of things based on where the sprayer impacts have taken place. Okay, this is pretty weird. Like, this is pretty cool. Let's take this further. So we got simulated VATs from Houdini and started plugging that in, and now we're thinking, okay, like this is the direction we're gonna go. So now, if you imagine this pipeline, a technical artist can take in this mesh, and they can decide what they want to happen in each region of space that is cleaned, whether they want it to melt, bubble away, crumble, change color, whatever. They can bake that into the vat and just iterate. There's no system change needed for this to happen. So we were pretty excited about this possibility. At this point, the material side, I tried taking a screenshot of it, and it's just too tiny on the screen. So I did this chunkier block diagram. So all we're doing is taking the world position of the fragment that's being rendered, reading from the place where Houdini encodes it, the position of the nearest pivot for the piece of debris, right? Because a piece of debris could cross the boundary between our voxels that we're creating, and you'd get these weird distortions, and they would kind of Gary's mod out on you. We don't want that. We want to apply the same animation consistently across a whole piece of debris, just based on where its center is in space. It's good enough. So we can therefore take all of that information, use it to concoct a UV for a volumetric texture, which is nothing fancy. It's just the 2D planes laid out in Y space, just a big long texture with all the slices in it. Yes, that's crazy expensive. We'll get into it. Read back some of the data from it, use it pretending it's the animation time, and then just plug into the material functions that Houdini gives us. It's got a rigid body dynamics informed by that material function. We are just lying to it about the state of the animation in certain regions of space, and we get this partial animation result. It's pretty cool. So we pull this into some bulk scenarios with these chain reaction explosions, and you can see here the voxel field of damage being built out in the debug view on one side. Hey, okay, cool. This will work for us. Like, this is pretty satisfying to set these things off. And then we got it in the profiler. And the results were displeasing. So a couple bottlenecks that we ran into. Draw calls. Game engines are pretty good at batching draw calls lately. It's one way to be CPU bound on your render, right? So the complexity of your scene typically will not bottleneck you on CPU unless you're having to just tell the GPU to do too much stuff individually, right? The way you can tell if you're throttling on draw calls without just pulling up the render profiler is change the resolution, and if you don't get frames back, there's a good chance that you're bottlenecked on draw calls. So meshes can be batched together, and the engine makes like an attempt to do it. The rough heuristic is one mesh, one material slot on that mesh, one instance of a material in that material slot, roughly one draw call. Not a universal rule, but generally, right? But the more you try to batch, you say, okay, I'm just going to take every object in the world that fits these criteria, turn them into one batch. It won't work, because occlusion also has to be calculated, and now you've got this big compound object you're drawing with a big complicated drawing box that's probably got tons of holes in it. So you have to be a little bit selective with it. But we found if we just kind of came up with a handshake agreement where we're just not going to send the numbers too high, right? It was 6 unique KIF materials, so like it's the same material code, but it's running with a different target mesh and target animation texture, giving us 6 unique Vesh variants. Vesh variant? Oh, goodness grief. Mesh variants per species. Creates enough visual variety, once you spin them around and scale them and stuff, you get enough variety for it to appear organic. That kind of tames the numbers for us quite a bit. Secondly, oh my goodness, I knew we were going to spend some VRAM on these volumetrics, but holy moly. Okay, so VAT animations, especially these crumbly ones, right? There's actually a lot of vertices to move around. They can get pretty chunky as well. So the handshake agreement is 1 vertex animation to spawn in a mesh. When we spawned in a colony in our edit demo, you might have seen these gross little meat noodles kind of working their way around as we grow in. Just 1 of those per mesh variant, please. It's okay. Like it's going to look okay. 1 destruction VAT per mesh variant, so we're keeping to kind of 6 and 6 and 6 and 6 and 6. Cost is predictable, and these volumetrics are still a huge problem for us. So we had to come up with a solution for this. The problem with the voxels, just in a sort of naive texture, is if I spray this corner of the room and that corner of the room, it's like 16 voxels worth of data, but I have to store it in 16,000 voxels of information just to cover the expanse of the entire room and the gaps between the regions with detailing, right? So we came up with this concept that we call Voxels. We divide space into fixed regions at a much coarser grained level of granularity. We picked 16 because it kind of worked. There's not a huge sort of intellectual exercise going into that. 8 was not enough, and 32 seemed like too many. That's it. So there's an extra lookup cost to read this voxel field because you have to look up, okay, I am in this really big region of space. It is Voxel number 7. Is there any information for me to read, and where can I find it? So you have to go to like an index structure to then find out what to read. You've got to tap RAM or texture memory a little bit of extra time. But now if I spray fungus in this corner of the room and that corner of the room, I just need to store information for those corners. And all the information, all the space in between, it's free. We can add cleaning data to it later, but it's free. So here is how it's laid out. Let's look at this. We're going to look at exactly what's happening in this GIF in punishing detail as we expand this slide. So we've got a spherical explosion happening that's adding a ton of damage into the voxel field. The top tile is an index tile that is in Voxel space. That's the big coarse grained, like which unit of 16 by 16 by 16 voxels am I in? I can go read that. It might say there's nothing there for me, or it might say, hey, actually, there's some data in this space. Please refer to tile 3 where your data is. Then there's a data tile per voxel that has information in it. It is an unaliased texture. It's data only, so reading it is pretty clean. We can just read exact pixel value. We don't need to do a ton of sampling. It's still pretty efficient to get the value out of this texture. And the one piece of data you need in order to evaluate it is to know what is the minimum bound in world space of the region actually covered by this texture, which it's inelegant, but we just feed that in as a material param. It works fine. The information happens to be updated in the same render pass. It's fine. So let's look at our operations here. So I mentioned computers are fast, but they're not that fast. But if you just need to naively read a chunk of data, it's totally fine. Just don't worry about it, right? So each of these tiles, these horizontal tiles here, is 16 by 16 by 16 times 4 floats times 4 bytes per float, exactly 64 kilobytes. And you can just blast 64 kilobytes from RAM over the PCI bus to the graphics card, no problem. You can do that a bunch of times a frame. It's fine. You're doing much worse things loading your bigger textures elsewhere in the world. This means that we don't have to worry about doing any fancy, really precise patching of this exact region, if this exact tile was updated, and figuring out byte offsets, and like, yeah, that's fun, fiddly, kind of Swiss watchwork programming to do, but it's hassle. You don't have to do it. The computer's fast enough for this. So our operations, let's see now. Our first voxel tile right at the top, the darkest blue one under the index tile, is receiving a ton of information. It's getting sort of the lion's share of this explosion in it. So we're seeing all the slices of this sphere appear in it. That's real easy. We just update it in place. Just blam, we'll blast the new pixel data into it, and it's immediately available to the material. To add a voxel, okay. This sphere that we painted into the texture exceeded the bounds of that voxel. You can see it kind of cuts off at the top. And the top of it actually ended up in a new tile. All we had to do to that is to write once into the index tile to just allocate a new tile, just say, okay, this region of space now has some information in it. Please refer to data tile number 3, and then write the tile itself. So 128 kilobytes to write that. It's totally fine. And then to update the bounds, all we need to do is update the material param that has the minimum bound, and then rewrite the index tile so that it's correctly oriented in that space. 1 param update, 64 kilobytes of data, no problem. So our finished material recipe, where I was praying this would not be too tiny, I might need to kind of gesture at it a little bit. This is for the exploder fungus, the kind of meat noodles that we were looking at. So just because this is a debris-based animation, we need to reach into it at the start and figure out the pivot of the debris piece there, which Houdini has helpfully encoded for us in UVs 2 and 3. Then there's a material function to read the KIF data at this region in space. Super cheap. There's 2 texture taps. A helper function that helps sort of output animation information. And finally, just the stock Houdini VAT rigid body material function. So we're just mutating our inputs to it. And the 2 little transformations we see in the middle, one is we're going to scale down those debris pieces as they fall. Just do that in the shader. Just wink them out of existence before we take the mesh away. And the other is something that, like, it's not super complicated math, but we're very smug about it, is simulating gravity in the shader. Because our game can have gravity off, it can have gravity sideways, it's got radial gravity, we get kind of weird with it. So we just add gravity in the shader so that it looks kind of in keeping with the other physics objects in the world. Okay, so we have gotten pretty far along with implementing this, but something still feels off. The big problem is that these VAT animations are completely illusory. They have, good news, no CPU time. Bad news, CPU doesn't have access to that information of kind of what vertices have been moved around. So our collision is completely unaffected by where you've cleaned at this time. And so because you're still, you're spraying a mesh and you're running down its little health bar, and eventually the whole thing falls away. Actually, most of the cleaning VFX was happening far away from where you sprayed, or kind of a foot to the right of it. So it felt kind of off, and you had like ghost collisions that you could run into. So we got a little ambitious. Remember when I said, like, there's no way this is going to scope creep, and we won't be still doing major versions of this like 18 months from now. So we thought, let's voxelize the collisions. If we, in theory, keep it the same granularity and resolution as the damage field, then we could, to start with, all that's got to be done on CPU. It's kind of expensive. Let's move it off to a background process. Unreal has some very handy tools in its task graph system for doing that, because spending time writing like thousands of voxels is pretty bad if you do it blocking the render. So then we'd end up with this additive field that is created as these meshes spawn in, just dynamically build a voxel field that we can use for collision. And then a subtractive field stored separately to that represents the places those voxels have been destroyed. And it's only that subtractive field that needs to be sent into the texture system. The collision side has more voxels in it, but it's only needed for physics. We never need to send that over to the GPU. Once we had this in, now For me, this is the moment where I thought, oh, thank God we can ship this. This is good enough. Don't need to come up with a whole new approach. This is working pretty great. Look at the precision we can achieve in the cleaning there. And just cut a huge swathe through these meshes. There's another example. We're even seeing the sprayer kind of be intercepted by some of the meshes and some droplets fly over the top. And now I can burrow, I can tunnel, I can drill downwards into a big colony. And suddenly they're very sort of dynamic feeling in the world. Okay, there's like 100 bugs that we still have left to fix at that point, but like, okay, this is shippable. This is like actionable. We can actually get this finished. So, little kind of retrospective. What went well here? I didn't mention it, but I think it is worth giving the team at Epic that worked on this kudos. We used the Unreal gameplay ability system as sort of the lingua franca for all damage that's dealt in the game. It's got a pretty high startup and learning cost, but it really, really paid off, because as we got more into these voxel systems, we were able to just intercept incoming damage events, inspect collision and radius information on them, and just slurp that data in and use it for voxel operations. Volumetrics ended up our most beaten up system. Mature does not mean elegant. It does not necessarily mean that the other systems are poor. I think they're pretty good. But it's mature in that when a problem occurs with it, you can generally assume the problem is with the content coming in, not with the system. We've solved a lot of problems in it and beaten it up a great deal. Our level designers, we revisit them with the tool that we provided them. Turns out they've built several variants on it that are pre-configured for different kinds of guide geometry they want to use. They've built like a cylinder that they want to grow on, and it's all tagged up, and they've built this whole palette of brushes that they can just drag and drop into the world to create some really interesting growth formations. And I'm very happy about that, because it's one thing to build a tool for your designers, and it's another if they say, oh, I patterned off it and built my own iteration of that tool that does precisely what I want. Okay, now we're cooking. This is great. We successfully never blocked lookdev because we had this separation of animation to the gameplay system. That's very successful. And finally, it's just absurdly nice to clean huge chunks of this off. Yeah, by the time we had the collision in, this is where I just realized I've been cleaning my own gym levels for like 20 minutes. And I'd missed the start of a meeting. So that part went pretty well. Retrospective would like to change or investigate in the future. I think we could take the KIF further. It's just got one level of sparseness right now, and that means there's still an upper limit to the region of space that it can cover that works for us, but it'd be cool to explore like a hierarchical approach with like a super big index tile that refers you to a smaller index tile, and that refers you to your data. Like, that would be kind of cool. Our blueprint for spawning, I think, worked pretty well for us, but it's still like a big script that's spawning actors in place. I think it probably would have been better in hindsight to have an approach where there's actual agents moving across these pathways and they're depositing fungus behind them, because then we could have them like hop off the pathways and improvise or fly at you or transition between networks. That's something I'd still like to explore. Doing more weird stuff with KIF, I think, would be really cool. We've got SVTs. Let's do weird stuff to like ferrofluid animations and mushroom clouds. I think that would be pretty neat. Expanding it for other fixed structures like structural damage, and potentially even using it as a generalized GPU volumetric. It's a pretty efficient way to dynamically update what is essentially a sparse volume texture, which is kind of difficult to manipulate at runtime. So why could we not store, for example, wind directions based on a room depressurizing and use it to animate kind of particles and stuff in the room? I think there's a ton of cool applications to explore that all are just, well, I will simply magic 6 months back into the schedule so we can do that, but maybe for Ambrosia Sky too. Your takeaways? The glue is kind of the creative part of this, right? Like we just took a bunch of existing stuff, VATs, volume textures, and just glued it together in experimental and high voltage ways to produce this experience. Some parts of it are inelegant, and I think this is the number one rule of engineering. Inelegant does not mean wrong. You might be asking with our voxel collisions, how do you create a simplified mesh that drapes over and covers all these voxels. We don't. It's like 10,000 cubes. It turns out the physics engine's fast. It's fine. Octrees are really good. It's inelegant, but we just never had to optimize it. It's fine. As I mentioned, the stock toolset can get you real far. The Houdini asset component can take you an enormous distance. With these, you can write these dynamic textures from Blueprint. It's only when you get to like productionizing the system that you need to start digging into native code and figuring out how you're going to make it run on an easy bake oven, right? Finally, what I learned as a technology leader in this project is that you can establish draconian build failures when the numbers go bad. You can do that. You can put technical barriers in the way of bad performance, but it doesn't actually help. You'll just bleed slowly until you hit that limit, and then you'll find there's 1,000 tiny things that you got to fix to get resource back. The real secret to getting your game performing well is you got to make people give a shit about performance. You got to make them care about it. It's a social problem. You got to make people think, I want to profile this. You got to put the numbers in front of them. Okay, you've successfully beaten the presentation. Thank you so much. I don't know if we have time for questions.
Yes, we do. Maybe just, no, yep.
Hey, great presentation. Good to see some games represented here. You answered most of my questions, actually, but out of curiosity, you said that the growth is happening as a vertex animation texture, like the squiggly arms growing and stuff.
Yeah, that's right.
What do the collisions look like? Are they already there, like the final, like, you know, when they have grown to the final stage, or do they update in real time?
Can you say the noun there again? It didn't come through the mic.
Oh, sorry. I just mean, like, does the collision update as they grow, or is there just the final stage?
Collision just updates to the mesh state, and it's fine. That hasn't been a problem for us.
Okay.
It would be cool. In theory, we could do like a growth vector and kind of lerp them in or something. It wouldn't be super hard, but it just didn't come up as a pain point for us. But I agree, in another context, another game may find itself needing to solve that problem.
All right, cool, thanks.
Thank you.
Anyone else? Yep.
Thanks, Jules. Really cool stuff. For the nav mesh, that fungal nav mesh, the space colonization, what were the determiners on the resolution of that space colonization? Is it the voxel / not voxel size of your fungus, or was it smaller or larger? What did you get away with?
They're completely independent. I mean, that mesh is, when it comes in from Houdini engine, we're able to, it comes in as a bunch of splines, right? And the splines are just a good way of embedding rotation and everything in each point. So we're able to look at it and produce like a tree structure of which spline branches off from which point on which other spline, and use that for all their timings. And that's pretty cheap. We're only operating on some subset of splines. So we actually we're completely free with that. We tuned it to the visual density we wanted. And then we do snap the meshes like to the voxel grid to kind of chef's kiss the animations a little bit, but it's not necessary for performance. It's just a bit of finesse.
Okay, cool. Any attributes on that, on those splines, were those just created in Houdini and read into the engine, or did you add them in engine? No,
we take pretty great care in the Houdini asset to preserve the surface information in these points, and ensure that like each point has the appropriate normal, as well as the appropriate position for the surface that it was placed on. And we try to weld those generated line primitives together as well, so you get like the longest possible spline is always one spline, and we kind of cut down the primitive count that way.
Awesome, thank you.
Thank you for your question.
Anyone else? Do you have the Steam Deck here with a level that we can try?
Maybe. I did not bring it. I'm sorry. I did not bring the Gabe boy.
All right, another time. we'll pay you a visit maybe.
Sounds good. Thank you
Okay.
so much, everyone.
Thank you, Jules.